Distinguished participants, thanks for joining this session. As the president of the International Astronautical Federation, it is my great pleasure to welcome you again to the IAF-GNF Space Conversation series. With more than 400 member organizations across 71 countries, including all leading space agencies, industries, societies, associations, universities, and institutes worldwide, the IAF has a really unique mandate to offer the space community a platform to connect and share ideas worldwide. And that since 70 years. All over the world, the International Astronautical Federation is actively supporting space activities and raising space awareness. Our mission is to share knowledge, promote international cooperation, and preparing the workforce of tomorrow. So we continue offering a virtual program free of charge to all the IAF community worldwide during the time, during these unprecedented times, which will still take a few months. But as you've seen, breakthroughs are coming. And we had a very, very successful IAC in 2020. But we, of course, try to share more information with you and interesting topics. And today, we will introduce to you the work of our member organization, Spaceland, and its first 3D printer Mars Habitat as game changer for planetary exploration. As you have seen in the last a few months and even weeks, we had very exciting space exploration missions. So it's a topic which is very, very dynamic and interesting also for the future. So thanks again for joining. I would now like to give the floor to Andreas Lindenthal, our Vice President for the IAF Global Networking Forum, and wish you an interesting hour. Please, Andreas.
Thank you very much, Pascal. Also a very warm welcome from my side, being in charge for the Global Networking Forum. I want to introduce into today's topic, which is organized by Spaceland Africa, which has already been mentioned by Pascal Ehrenfreund. And the background, of course, is that effective development of habitation and building technologies for in situ resources utilization for human habitats on the moon or on Mars is becoming a top priority at international level, because a sustainable outpost in such a hostile environment will be needing, let's say, effective solutions in engineering, in operations, also in order to allow effective operations on these in these situations. So the panel discussion of today will highlight, let's say, container and the content of the Spaceland Center activities, which is a one-to-one pilot project showcasing in order to demonstrate, let's say, what are the effects of having, let's say, this kind of habitats in those planetary environments. And I'm really looking forward for an extremely interesting discussion. Therefore, I'm pleased now to give the word to our moderator of today's session, Dr. Carlo Viberti, President of Spaceland Africa. Thank you. Please, Carlo, it's your turn.
Thank you, Dr. Lindenthal, and thanks a lot to Dr. Feitinger and Professor Ehrenfreund for having us here. Actually, Spaceland Africa is a reality that exists already for a few years, and today we'll be showing to you in the next 20 minutes some of our, let's say, ongoing activities for the new, let's say, perspective for a habitat on Mars. So let me try to share my screen in order to provide some more data on what I'm talking about. Do you see my presentation here? I think it's visible. Okay. Well, first of all, as a moderator, I have the duty and the honor to tell you that you can interact into this panel by addressing this website here and inputting this code in order to ask questions to our scientific committee that's going to follow me. We're going to talk actually about something rather unique worldwide. We have identified in several locations worldwide, as I said, a few ideal environments for the design and development of a Mars habitat. And Mars habitat, which has a very important implications, so to say, with everyday's life. You see here a view on about the ongoing field works for one location in Mauritius, but we have identified a couple of other locations also in Europe to develop our first concepts. What I'm talking about is capitalizing on the previous records of Spaceland, as probably some of the other IF members know. With the mother company Spaceland Italia, we've been setting a few records in weightlessness, and they are summarized here by flying test subjects also for Nobel Prize winners for research with people as young as 11, as old as 93 years old, and also the first woman with disabilities. Apart from myself, all of this activity brought very important results also in terms of neurobiology, basic studies about Alzheimer's and so on. All these expertise now we want to capitalize it, and this was done with, for instance, the Nobel Prize winners group, European Brain Research Institute. All of these activities, all of these, let's say, expertise is now concentrated into this new project that we are developing. And this is one of our test sites. This one has been identified thanks to one of our top level engineers, Dr. Dini, in Italy, but a similar one, as you saw, is also Mauritius. It's very important to find a place in which you can really test one of the major concepts here, which is ISRU, a Mars habitat, but this is also good for applications on the ground on our planet. Mars habitat has to be built with the maximum use of ISRU, like architect Petraroli later on will explain you. And the other concept I want to talk to you about, not only utilizing local resources and say local materials, but also we have to maximize what is called NZEB, near zero energy building concepts, which are good both on Mars and also on this planet in order to minimize the consumption in habitats. I would also say near zero risk. This is another acronym that I kind of invented for this, because we have also to take into account that on Mars, we cannot have very tall buildings or very high elevation structures. We need to cope with galactic cosmic rays, solar wind particles, dust storms, meteor impacts. And in order to do this, we, as a Spaceland group of engineers and architects and scientists, want to make sure that we can capitalize on our knowledge about low gravity STEM, science, technology, engineering, and medicine, in order to make a habitat that can be coping with all these issues and therefore minimize the risk. That's why I called it near zero risk. That's why what you're going to see with the architect Petraroli in particular, those tall buildings that NASA is considering, to our knowledge, are not really ideal. And we want to simplify and flatten the dome-shaped structure of this new habitat on Mars we are designing, we are going to develop. And of course, we're going to use Mars regolith because we need to maximize, as I said, the ISRU, and it would be a kind of composite between Mars regolith and polymer. And to do this, we also use a kind of a steel proprietary to be developed mixed technology, inflatable and 3D printing. And all of this will allow us to focus on quality of life for the astronauts and also working and nutritional aspects, which are top level standards for us. So this habitat has to be safe, secure, easily to be, say, produced and generated. And the mixed technology we're talking about here will allow us to develop a flattened dome-shaped series of habitats, which according to us are the best way to cope with all those risks I was talking about. It is one of the artist's view of the prototype you're going to build in those terrains you saw. And near the terrains, there will be also academic and business headquarters. So you see here, these are NZEB buildings, so of course, high-tech earthbound constructions. But to the top right of this image, you see again that near to this academic and space business headquarters, we will have this dome-shaped structure, and we have the Mars habitat we're talking about. So well, let me then remind again for the questions of this website, and in the meantime, I have the pleasure to introduce our expert in in medicine, which is Dr. Nando Goswami. He's going to talk in the next 6 minutes or so about the analogies between commonalities between astronauts, especially people on Mars, and what we can say are the aspects of medicine that put our space very close to the geriatrics issues that he's going to talk about. Dr. Goswami, the mic is all yours.
Thank you so much for your introduction. I hope you can see my screen. I would just like to say thank you again to Carlo and the team for presenting this theme. I think it's a very exciting theme. And my name is Nando Goswami. I'm a professor at the Medical University of Graz, and I'm leading the research unit called Gravitational Physiology, Aging, and Medicine. That means we try to combine to see how space flight and medicine could be related, or what is the relationship. I'm also a member of the IAA for the last 7-8 years now. But we all agree, before we even go to habitate somewhere, we all agree that we are used to life on Earth. That means we are used to life in the gravity situation. So, and if you really want to see the gravity dilemma, that means for millions of years, we are used to life on Earth, and then suddenly we decide to go out of this Earth's 1G, let's say, to space. We also have to be aware that we are going to subject our body to a lot of hypergravity when we leave, and also when we begin to enter either the Earth's back or the reduced G environment of Mars. But one thing we must not forget here, when we think about the human being on Mars, before we reach Mars even, I think there is a big story in between, because until today, we don't even know what happens to the body for so long in space, because the most studies on that have studied humans in space have 60 days, 100 days maximum, but we all know that the minimum you will need to go to Mars is around 6 months when it's in this closest position with the current technology that we have. Now, this particular figure here just shows you that just being in space for a few days or a few hours, you can see on the screen here, affects you a lot of different systems, and you can see a lot of different systems begin to react just because we move from our normal gravity environment on Earth to space. And this has quite significant effects on the body. For example, you can see the different systems. But one thing you will notice, and that's why I love the human body, because whatever you do to the human body will find a new balance. And it does. Actually, being in space, we noticed that about 1.5 months, you kind of get adjusted to the new environment, which is not the environment on Earth, but rather the environment in space. And so you have kind of accepted that new level that we are in space with microgravity, which means there's really almost no gravity, just minimum. And so your body gets kind of used to that, and it has really massive effects on different systems. For just to give you an overview, the picture here on the right-hand side here will show you that these are the bone losses we have per month. That's about 20% of the bone on which we have all the muscles are actually getting lost. To give you an idea, and a typical old lady loses about less than 2% per year. The astronaut would lose about 20% per year. And if you look at the bones carefully, those bones are mainly in the lower part, which means the chances of fractures are very high. And the same goes for the muscles. The picture on the right-hand side shows what happens on Earth when we stand. We are standing pretty much straight, but in space, we are actually like in a baby position. And because of that, all the muscles of the leg, which are really our best friends, when we stand up on Earth, they are pretty much gone. You really have a massive muscle loss. And this picture here just gives you an overview about the fluid shift. This is when you're on Earth, a lot of blood is in the lower parts. Why? Because of gravity. And then once we go into space, we kind of, the second number here, you can see fluid moves towards the upper part. After a while, we get adapted. But the problem is the moment we come back to Earth or we land on a planetary body that has, let's say, different gravity. For example, Mars, we all know, has like 1/3 gravity of that of the Earth. That's pretty heavy on the body. That has already been pretty much, to use the word, deconditioned by spaceflight. And so you have these classical pictures, and I think most of us that work in spaceflight already know this. You have happy, smiling astronauts, but 6 days in space or 1 week in space, that's the classical picture that happens. They just can't stand up. And of course, all what I have just told you about what we call deconditioning is happening. I mean, if this is what happens to us after 7 to 10 days in space, what would happen to us after 6 months in space? And then we land on a planetary body that has some gravity. We'll either fall or break a bone. So up to today, we don't even have the knowledge that how will the systems react. In other words, if we were to stand up, let's say when we land on a planetary body such as Mars, how are we going to be able to cope? How is our heart going to cope up? How is the muscle in the leg? How is the blood flow to the brain going to cope up? We just don't even know any of these things. So there is a lot of massive research that has to be done also. I mean, apart from we don't even talk about the cosmic radiation and other effects. I'm talking pure physiology. So we try to understand what really happens if people are lying down in bed. But like I said, until today, we don't even have studies that have ever showed that if we are to reach Mars, what would happen to us. So here we try to do the sit to stand test, in which we try to understand what are the systems that would change, for example, here in people that stand up. And so there is still a lot of lack of knowledge that we just don't have. There have been some studies where they have done partial simulations of gravity of Mars, but those were for short-term effects, not even long-term. And I think this is really important. And for me, I like to see space beyond what we can use it, because I like to see the role of space for life on Earth. So I actually combine the knowledge that we learn from spaceflight for life on Earth. And how? Because the lying in bed is actually a model for a space flight. We spend tons of money on putting young, healthy people in bed by ESA, NASA, all over the world, German space, just to see how the people will react after lying in bed. But the old man or the old woman is lying in bed anyway, because they are either sick or they have a broken bone. So they will go down much, much faster. And we must not forget that they were not astronauts before they were admitted to the hospital. So this is what I combine. And I think that making a colony on Mars is really important, but we have to understand the physiological deconditioning on Earth so that it can help us understand also life on Earth. Thank you.
Thank you, Dr. Goswami. What you have been addressing now, it's really a huge area of doubts and concerns and challenges. Therefore, there's a lot of work to be done. And we are really looking forward to be able to keep on developing new strategies with you in our Mars habitat. And as a matter of fact, now one more challenge we have is not only to keep people fit on Mars, but also to have them eat good and feel psychologically well. That's why it's very important too to have within the facilities that are inside the Mars habitat, and you're going to see some of them through Architect Petra Rolli's presentation in a few minutes. We have a robotic greenhouse. The robotic greenhouse will most likely be done through the support that we are getting from top-level scientists, engineers like Professor Zhang that is going to talk in a few seconds. Just wanted to remind everybody that there is this Lido facility, and we have actually already some questions coming in. I think I'm gonna ask this person that are putting all these questions. Some of them are extremely interesting to reply to bear some patience, to bear with me, and we'll try to address all the questions at the end of the session. Mm-hmm. So for time being now, I will switch the mic to Professor Zheng Jin from the Center of Space Exploration, COSE, it's called COSE, of China. And he's actually the lead engineer that was in the team that put the first biological experiment on the dark side of the moon. So we do have one of the best experts in putting new life on an extraterrestrial planet. Let me show the presentation of our guest. In the meantime, Professor Zheng Jin, can you hear me?
Yes, I can. I'm here.
Okay.
Okay, I can start. Okay. Hello, okay, everybody.
Please. Go ahead. Yes.
Hello, everybody. I'm happy to meet you on the internet. I'm come from China. I'm the chief designer of the chief designer of the first biological experiment on the dark side of the moon for the space mission Chang'e, the Chang'e missions.
Okay, can you see the second slide, Professor?
The second slide is that here is our payload. It's on the Chang'e biological missions. The payload weight is just about 2.68 kilogram, and the first side just about the diameter is about 173, and the height is 198. You can see here.
Can you see it?
Yes, I can see. Yes, I can see. Okay. The biological space is less than 1 liter. You can see the red color on the land is our payload positions. It is upside down the land. On the top of the tank, you can see a type. This type is for the sunlight from the lunar surface. The light will go through into the tank for plant to photosynthesis. Okay, the next.
Okay.
In our payload, there are 6 species. Plant produce the oxygen, animal consume oxygen, and produce the carbon oxygen. They formed a micro ecosystem. So there are 6 species, and we sealed 1 bar atmosphere and 18 gram water and 20 gram soil into this tank. It take from the Earth. At 11 p.m. Beijing time, January 3rd, we water our payload. Then the seed growing. Just one day later, cotton seed sprout. And you can see this picture was taken on January 7th. You can see that the root of the plant is horizontal direction, and there grew 2 leaves on here. Okay, the next. When our experiment successful, media oppressed it. Just like Nature said, it is the pioneer experiment. The science said it is the first for humankind. Plants are growing on the surface of the moon. So we do this very successful. When here is the next. Here is the construction principle of controlled ecological life support system. Our payload is designed according this diagram, such as this. The next, you can see the small payload we have done successful on the moon, the far side of the moon. The next, we will do some experiment. We enlarged the payload for 100 times to do this experiment on the Earth first. And we proposed to a room, a moon, or far, or a Mars garden for astronaut. When the astronaut can take breath the air, the oxygen that produced by the plant on the moon and Mars, I think the astronaut will be very happy and will be healthy. So we should build a garden for the astronaut. Then we formed the conception idea of the build Mars habitat. There are 3 circles. You can see the under left of the picture. There are 3 circles. Innermost, there is the living room. It's very safety. And the mid circle is workplace, such as factory, laboratory, and so on. The outermost circle is the Mars garden or Mars farmer. It can produce the food and oxygen for the people who live on the Mars. Sure, the 3D printing technology is very important for building it. So this is my work shared to you. Thank you very much.
Thank you, Professor. Thanks a lot, and extremely interesting. And we will certainly find a way to accommodate all your requirements for this hydroponic greenhouse inside one of the environments, even on our ground model. Actually, talking about ground model, I would like now to, since time is running and there are a lot of questions coming in, to quickly switch over to architect Celeste Petraroli. She is the leading architect for our development of the habitat, and I will introduce her by directly switching to the presentation, which should be somewhere here.
Right. So let me introduce you a quick view on Mars habitats design. As we know, designing habitats for Mars means faced with 2 main constraints. The first is the unfriendly environment, and so we need to think about how building materials dramatically change their behavior in such harsh conditions. That is also true for electronic devices that can have trouble if they are exposed to very cold temperatures and dust storms, and also radiation. The second constraint, sorry, I cannot go ahead with my presentation. Right. The second constraint is the huge cost of delivering materials and hardware from Earth to Mars. That's why designers try to use as much as they can the in situ resource. To have a glance of what is going on worldwide, we can refer to NASA competition of 2017 and 2019. Here we have 3 finalist proposals in which we have a small modular habitat, a tall tower more than 10 stories high, and an entire city, as you can see, an entire city with habitats underground and a huge sphere with a forest inside. These are very amazing proposals, but we think there are still some issues to be solved, especially referring to radiation proof, to micrometeoric impact proof, and also the dust storms problems. Yes. For parametric architectures and robotic aids, with that we can construct such amazing structure as you can see in these pictures. And of course, we have to think at the holistic environment for astronauts, because as we saw before, they need to stay for a long period on the planet, and so they need to live in a more health-likely, with habitat, with natural light inside, ergonomic features, facilities for fitness and wellness, and surrounded by natural elements. They will be able also to eat very fresh organic food thanks to hydroponic robotic greenhouse. And now going to our proposal for the habitat, we think that a flat structure with a very simple dome shape will better resist to the radiations, the dusty storm, and the meteoric impact. We are setting a new building process without outdoor construction hardware. That means a mixed use of 3D printers and inflatable structure that allow us to avoid the presence of human operators outside. We will use in situ resources, and we will have a concrete made of regolith, water, and some binders, of course, with polymers too. And the 3D printers will be used for all the indoor structures. The configuration is about a main astronaut hub connected with the robotic greenhouse and with the astronaut's private room. Our philosophy is to recycle everything, also human waste, on site. Going ahead, in the plan view, we can see on the top of the dome some photovoltaic panels for the power supply and the radiation-proof skylight for natural light. And if we go on the cross-section, we can see the inside activities. We will have several rooms for laboratories, meeting room, management offices, a training center inside, and the core underwater tank for microgravity training of the astronauts. Going ahead, we think that astronauts need to have trained on site close to the long period of permanence. If you want to have a look of how it will look like from the inside point of view, this is a picture of a main control room, our laboratories, and a training area for astronauts with the multi-axis facilities. And the main tank will look like this one. This is the tank that Dr. Ruberti did for ESA several years ago with the Columbus mock-up inside. I'm very sorry for the problem we had, and I thank you for your attention. Please refer to our website for more questions. Goodbye.
Thank you, Architect Petraroli, and I'm sorry for this mishap. There was a glitch in the connection, but you know, we managed. We are not on Mars. In the meantime, there are a lot of questions. So if you want, I can pick a few of them up, letting free all the other speakers to intervene if they want. There were also questions about the size of the 3D printers we're going to use, and these 3D printers are still being sized according to the diameter of these habitation modules. We are talking now about 10 meters diameter for the actual complex of 3D printing, but there's also a question of the pressure inside versus the material we're going to use for the inflatable structure. Because as I told you, we're going to use a kind of mixed technology, inflatable / 3D printing, using as much as possible ISRU, namely the composite regolith / polymer. And there's a lot of calculations, structural calculations being done to understand what is the best process vis-a-vis also the time of the drying of this regolith-based concrete on Mars. And the same problem, I think, is going to be faced for the astronauts on the moon. But we want to go straight to Mars. There are different considerations to be done according to the different gravity field, the 1/3 gravity versus 1/6 on the moon. But this system, it is answering one of the questions, can indeed be utilized also on the moon as well. But the Mars habitat, therefore, will be a kind of showcasing habitat for also moon applications. I'm looking to my offline telephone to get other questions that I didn't reply yet. The pandemic situation, how did it impact on our project? Actually, the impact was pretty bad as far as Mauritius is concerned, because we had basically lost 1.5 years in total. Last year because of a little political turmoil in the island, and this year because of the pandemic. All the activities have been slowed down, and now we are concentrating more, since we cannot travel back and forth so easily, on developing the engineering concept with several universities. And in particular, we have, I want to thank also Professor Gallina from Trieste University for the greenhouse, which we're going to develop together with Professor Yang Jing from China, as you just heard, and also Professor Paolo Maggiore from Torino Engineering, because with them we are optimizing respectively the greenhouse and the actual construction process, materials versus technology. Let me also pick up some more questions. I want to show you just a couple of minutes of video in the meantime, in order to see live this development. The development actually would be based on a double approach. The double approach meaning that we're going to have also an academic and space business, academic versus space business headquarters. And for that, we are going to actually, let me share this one. We're going to have this configuration of a 1 hectare. This is academic versus space business incubators and headquarters nearby the habitat territory. It is a night view of this high-tech drywall technology for the actual buildings. This, of course, on the ground, but it's also important for us in order to gather all the intellectual communities for the next, which is actually the terrain which we're going to develop the Mars habitat. This is one of the inner environments, and the Mars habitat would be nearby this academic and space business headquarters. As I said, we want to maximize the dome-shaped approach, and differently from the winners from the NASA competition, we think that these very low-profile dome-shaped flattened structures are much better in order to minimize the risk of impacts from micrometeoroids or meteoroids even, and also to minimize exposure to the galactic cosmic rays and to the hydrogen particles, the solar wind heavy particles coming basically from over the planet on Mars. It depends also on the elevation and where the habitat will be located, but the lowest possible the structures they are, the more flattened dome shape they would be. We think that would be also good in terms of protection, and also to minimize the energy consumption, and the thickness of the walls is also important. The regolith / polymer composite had to be at least 1 meter thick. So we think that this is the best configuration to actually be able to protect the astronauts inside. So I think that this wraps up our presentation.
So thank you very much, Professor Weberti. So let me shortly thanks everybody for the contributions to this very interesting and exciting insight of the activities covering the physiology of the human bodies to be considered on such a long-term mission, the biological habitation aspects which have been addressed, and the various design solutions. All that was extremely interesting. And so with a thank to all our speakers who were contributing, I would like to thank all the participants for the participation. So this was the last of our GNF sessions. And I would like to take the opportunity to wish everybody all the best for the upcoming holiday season. So stay safe. I would like to give special thanks to the team of the IAF Bureau, who is organizing all that in a perfect manner. And I would like to see you back in January 21, when we are putting a special focus on the next interesting subject. So until then, please stay safe and take care about yourself and your beloved ones.
Thank you.
Thank you very much.
Thanks a lot. Goodbye.